So last class period we started talking a little bit about exponents, kind of what they were, and how to simplify some real basic, like if a squared shows up, what do you do with your, your numbers? You multiply them together. Cubes, like you were talking about earlier, Trey. So we're going to delve a little bit further into properties of exponents and how to deal with them when there are variables involved in particular. So the first thing we're going to look at is 7 basic properties of exponents. Some of them, I'm sure you've seen all of them at one time or another, but some of them are easily confused with each other. And so I want to make sure that you understand which ones work in which ways. So our first property of exponents is when you have the same base and you have exponents on those bases. So in particular on this one, we have a to the m times a to the n. And does anybody remember what you do when you have those two multiplied together? How you deal with it? Yeah, you add the exponents together. So this actually results in a to the m plus n. The exponents could be the same, they could be different. And I will never ask you to justify why these are the case, but I do want to justify for you why briefly as we go through them, because I hate it when math looks like magic, or it looks like something somebody just made up. There's actually concrete reasons why this works, and I want to give you some feel for the fact that this isn't just made up stuff, okay? So let me give you a really brief example of what happens when you would have a very specific problem. If you had a cubed times a squared, and you didn't remember or didn't know that this should be a to the 5th, a cubed, we talked about last time, means that I have a times a, right? And a squared means I have a times a. And if you look very quickly at what exponential properties mean, how many a's are there here? There's 5 of them. So that's where this is coming from, okay? Not made up at all. Now, if when you multiply, you end up adding exponents, what do you think is going to happen if you divide? You subtract. And again, let me justify for you why that's happening. So the y on that, let's do one that's a to the 4th over just a. Now just as a reminder, if a is written all by itself like that, it means it has a power of 1, right? So a to the 4th means I have 4 a's. A to the 1st means I have 1a. And then I can reduce the word you guys like to use, the word that's probably been sort of ingrained in your head is the word cancel. It's a horrible word because sometimes we say cancel and we mean that it actually divides to 1, and sometimes we say cancel and we mean that it adds to 0. So it's not a great word, but we do divide this out, and I'm left with 3 a's, which is actually a cubed. And again, the way that we got there was because there's a 4 here and there's a 1 here, and when you subtract 4 minus 1, it gives you the 3 we ended up with. So that's why that property is working for us. Number 3 kind of looks like number 1, right? I've got a power of m, I've got a power of n, I've got a base of a. What's different about 3 and 1? There's parentheses. What else? There's something else different. You got an exponent outside the parentheses, but there's something that the second one here, number 3, has that the first one didn't have, or did have, like it's missing from the third one. Another a. Okay, do you guys see that? On the first one, there are 2 a's in the value, right? You see a and a, it's written twice, but on number 3, you only see it written once, okay? So that's also valuable to recognize that those are different in that way. So this is not 2 bases with 2 different exponents. This is 1 base with 2 exponents, okay? So I know you guys know what it is, at least some of you do, so tell me what you believe that this is going to be. What are you going to do with those exponents? Multiply them. That is correct. You're going to multiply the exponents. So let's talk about why that works as multiplication here, whereas before I ended up with addition. So let me use that same 3 and 2 that I dealt with before, and we'll write it like this. So a cubed means I have a times a times a. And then if I square that, it means that I would have a times a twice. Right? But how many a's did that end up giving me? 6, not 5, right? So if I have an exponent raised to an exponent, I think that's how Josh was describing that, this idea of that exponent having an exponent on it, I end up multiplying the exponents together. Okay, am I good to switch screens? Anybody still need this one? Okay. Former properties. Number 4 and number 5 are quite similar. On number 4, you're going to use a word that I'm going to tell you can't use after you use it, but let's use it now anyway so we can get it out of the way. What do you think this is going to become and why? You know what it's going to become. Somebody tell me. What happens when I have AB to the M? Somebody's saying it. I hear it. Josh? You're trying to think. Do you know? Okay, what do you think, Macy?
It might be like A-N and then B-N.
Yes, you are right. And the process by which you did that is what you guys would like to call what? Distribution is the word you want to use. It's the word you want to use. It's not really what's happening. Distribution is a very specific property of multiplication over addition and subtraction, but it has the same sort of feel to it, right? Yeah, it does have that same sort of feel. So let me show you why this works. So we'll just do it to the power 3 so that we can write it down pretty nicely. So this is AB times AB times AB. That's what the power 3 would mean, right? It is. And one of the properties that we learned back in the section on real number properties, I think it was section 6, is that you can do multiplication in any order. You can regroup things together, right? We called it the associative property and the commutative properties. So we can reorder these things to put all the A's, if you will, kind of together, and then all the B's together. And if we do that, then we can quickly recognize that this is A cubed and B cubed. And that's because of properties of associativity and commutativity. Okay, so if that's what works with multiplication, what do you think the division one's going to look like once I simplify this? The same, you're right, Megan. It's going to be A to the M over B to the M. Again, it feels like the distribution property. And again, if I look at the reason why, I'll use that same power 3 that I did a minute ago. This is A over B times A over B times A over B. This is kind of like that one that you were looking at, Trey, with numbers in it, right? Yeah, very, very similar. And I end up with A cubed on top and B cubed on bottom. Make sense? All right. Does anybody know what anything to the 0 power is? Good guess. It's actually 1, though. A to the 0 is 1. 5 to the 0 is 1. 15 to the 0 is 1. We don't talk about 0 to the 0. That's not a defined operation. But any other real number to the power 0 is 1. And I'd like to justify for you why. And it looks a little bit funny, not quite as straightforward of a justification as the others have been. But I'd like for you to take a to the 0, and instead of thinking about it as 0, and you could use any number you'd like. I'm just going to use 3 because apparently I like 3s today. But 0 is the same as 3 minus 3, right? Sure, no problem. It's the same as 3 minus 3, 4 minus 4, 6 minus 6, I don't care. Pick your favorite numbers. If I go back to property number 2, and I use it in sort of reverse, like this, I could change a to the 3 minus 3 so that it is written as a cubed over a cubed. It's using my property sort of in the backwards order of the way I normally do. But you tell me, what happens when I have a cubed divided by a cubed? It's just 1, isn't it? Yeah. So anything to the 0 power is 1. Number 7 shows us what happens when we have negative exponents. Virtually all of the time, it would be an odd situation indeed, you are told to not have negative exponents in your answer. Simplify it so as not to include negative exponents. So you need to know what to do when you have negative exponents to sort of get rid of them. So the way that you deal with that is that you actually switch it to the denominator. And if it were in the denominator, you would switch it to the numerator. The negative on the exponent will go away when it's moved into the denominator. Okay, again, okay, great, but that sort of seems like, smoke and mirrors. It does feel a little bit like that. But it actually works out very similarly to number 6. If I have a to the negative n, that would actually be the same as a to the 0 minus n, right? That's what negative n means. It means 0 minus the value. And if I use, again, property number 2 in reverse, that means I could put a to the 0 on top and a to the n on bottom. What's a to the 0? It's 1. We just proved that, didn't we? So there's the 1 over a to the n that we claimed it was. Okay, so whenever I talk about the explanations of these things, sort of everything here on the right-hand side on both of these slides, I undoubtedly have students who want to start doing that on the problems. That's not the goal. You've got the properties, you've got those rules, you've got those, whatever you want to call them, you use those. I'm just justifying to you why those actually work. Okay? So we're going to do some examples. Some together, somewhere I'm going to give you guys an opportunity to write on my iPad and practice too. So we'll start with the first few and do them together. Most of the cases are going to involve more than one rule at a time, not all of them. But if you're taking a look at this one, this is very similar to property number 1. There's just 3 terms instead of 2. But it can be extended to be 3 terms. This is no big deal. They all have the same base, right? All have base x. So my base will be x. What would I do to get my exponent on that base? Add all 3 of those numbers together. So what is 2 plus 5 plus 4? It's 11. So this is x to the 11th. Okay? Not really even any work to show on that. There's going to be work on some of these, but not on others. Now on the next one, you'll notice that there are coefficients. There are also bases, right? I have the base of y in these problems, but I also have some numbers in front of them. I have a -4, a -3, and a -2. Now properties of real numbers let me regroup things, right? I can put all the numbers together and I can put all the y's together. Right? That's what properties of numbers let me do. And that's what happened a couple sections ago. So I can actually focus on just the numbers for the moment. What is -4 times -3 times -2? It is 24 and it is negative, you're right. And once I've dealt with it, now I can turn my attention to the y's. They all have base y, so they all can be combined as well. I have y squared, I have y cubed, and I have y. So how many y's, or y to what power, will I have? 6. Okay, now 3 is nice in the sense that there's no negatives involved. Kind of like that. You don't have to deal with it. But what do you notice is different about 6 besides the negatives than about number 3 than about number 2? There's x's and y's. Very good, 2 variables. Okay, so when I'm dealing with this, I need to be careful to only combine the x's with x's, right? And to only combine the y's with y's. But all the numbers can be combined before I begin any of that nonsense, right? They can all be combined. They're all like. So what is 6 times 4 times 2 times 3? Feel free to grab a calculator if you would like to double check that. 6 times 4 times 2 times 3. 144 is what I have as well. Did everybody get 144 on that? Okay, now, generally speaking, alphabetical order is what you see people write this next part down in. There's really nothing special about it. If you want to write Y and then X, I mean, more power to you. But most of the time people like to keep alphabetical order and they'll put X and then Y. So how many X's? What power will my X have? A 4. And then I'm going to put my Y. And what power will my Y have? A 5. Okay, you guys are totally on a roll. You feeling good about this? So far? So far, so good? Okay, so I told you I was going to do a few of them with you, which we did, and now I'd like for you to try some on your own. Different properties are at play as we keep going. I'd like for you to do 4, 5, and 6, and then turn to a neighbor like we've done recently in class to compare your answers. Near the end, compare with your next door neighbor. See if your answers match or if maybe one of you has missed a step along the way. You guys want to volunteer for me? First one? Do for me? Thanks. Oh, yeah. Okay, so you can write with either tip on the pen. You just have to hover when you write it. If your hand touches it, it will write on the screen as well. Okay, Chloe's going to do number 4 for us. Check and see if you have the same thing she does. x to the 8th. The step before says 2 times 4. It's kind of hard to see. I know the iPad does that sometimes. Yeah? You want to do the next one?
Yeah.
Okay.
Fun.
All right. Macy's got the next one.
I like this. This is fun. Okay.
Did I get that turn? Yeah, it's on.
Okay, it's on. Okay, so.
Very well done. Did anybody, you don't have to show of hands, but just think, did anybody forget to cube the 4? Because that's a really common mistake on that one, is to sort of forget the coefficient part of it, applying to the cube applying to that. Okay, so you want to remember that the 4 will be cubed just like the u is cubed. Who'd like to do number 6?
I'll do
Over
it.
here.
Someone else wants it.
Oh no, I'm going to volunteer somebody else.
Aw,
You already got a
I like
volunteer.
this.
All right,
Is,
Sarah, I'll come back to you. You're all right.
Like it's actually
Okay.
fun to raise words.
Number 6. Very well done. 27 x cubed y to the 6th. Does anybody have any questions about these 3? Places where you're not sure how that happened. Okay. Let's try 3 more. Or 2 more, sorry. 7 and 8. These are a little different because they're fractional. Done. Compare with a neighbor. Who'd like to put number 7 on the screen for us? I'll check and make sure the right answer before you do it if you want. You can do it, Preston?
Oh,
You raised your hand for me.
No.
I heard you talking. Oh, come on. I'm pretty sure you had it right. Let me see who you have. That's perfect. 7 looks good.
All right, go Dad.
Well, just do your best. This side actually works smoother if you write it on that one.
Okay.
Okay.
So, can I just write down the answer or should
Yeah.
I work?
You can
Okay.
write it down. If we have any questions, I can do the working out part. Okay. person has the right answer. He has applied the cube to every piece. The reason it's negative is because I have 3 negatives, right? So I'm going to multiply negative, negative, negative. I end up with negative. 2 cubed is going to be the 8 on top. And then I have a cubed and b squared cubed. Multiply exponents to give me b to the 6. Any questions on that one? More going on than the last ones, right? How about 8? Who'd like to do 8 for me? Macy's like, I want it back. All right, Macy, we'll let you have it back on this one.
This is fun.
This part is fun. I don't know why it is, but it is.
Okay. There's one more step. Can somebody
there's one
help
more step?
Macy with
Oh
one
my
more
gosh.
step she could do with the 14 and the 35? Alyssa. Yeah, what do you see on that one, Alyssa? All right, how come? Because that's what it said in my calculator. Wow. True, but probably not our best answer. Any ideas as to why the calculator would have gone that route? Divide by 7. Okay, that's a better one. All right, so both 14 and 35 are multiples of 7. So if we divide each of them by 7, we'll get the 2 on the top and the 5 on the bottom that the calculator will in fact say, you're right, to give me 2 over 5y.
Yeah, that's okay. I didn't know that part. I forgot about that.
Alyssa's just saying what half of you did, right? I know she is. All right, any questions on that one? The x's cancel, right? Or they reduce, they divide to 1. All right, I'm going to do the next couple with you. Number 9, very similar. There's a couple of different ways that you could view and think about number 9 and number 10. One way you could think about it, I'll just show you a couple options and you can decide on which one you like. So you might want to just watch for a second to decide what you want to write down. One way to do this is to think about, if the numbers are small enough, what you actually have. I have 2 x's and I have 6 y's on top, right? And on bottom I have 1 x and I have 2 y's. And then I could do it almost like what Macy did in that last one, where she was just reducing the pieces they had in common, like this, right? One more. Which leaves me with an x on top and how many y's? 4, right? Oops. And that's totally fine. There's nothing wrong with doing it that way. You can totally do that. Good with that. Something else you could do, if you want to think about it more from some of the properties that we were looking at, is you could recognize that this is a 2 and there's a 1 right here. That pink is really not dark enough. Let me try a little bit darker color. There's a 1 here and there's a 2 here. So if you're looking at those, you could actually say that I've got 2 minus 1, x to the 2 minus 1. And then looking at the y's, I could do y to the 6 minus 2. 2 minus 1 is 1. 6 minus 2 is 4. It's another perspective on how to do that. Okay? So a couple of different options. I don't care which one you do. Both of them are totally valid. On number 10, I'm going to go with the, well, actually, let me show you something different on number 10 before I start. On number 9, you'll notice that the exponents on the top were larger than the exponents on the bottom. And it's actually reverse of that on number 10, right? The exponents on the bottom are actually larger than they are on the top. And it could be that you have some higher on the top and some higher on the bottom, like a mixture of those two possibilities as well. This is probably one of those cases where, again, it might be a little bit cleaner to write them out. So let me do that way first. I have a U, and then I have 2 W's. And on the bottom, I have 4 U's and 6 W's. And then if I reduce what they have in common, one of my U's is going to go away, and 2 W's from the top and bottom. So what do I still have left on top? A 1. Remember, I'm dividing here, and when you divide something by itself, you get 1. So there's a 1 on top. I have 3 U's on bottom, so that's U cubed, and I have 4 W's on bottom, so that's W to the 4th. On this problem, this particular method might be a little bit cleaner, but I am going to show you the other method just so that you're aware of what it would look like. So again, there's a understood 1 on that u. So this would be u to the 1 minus 4. And then w to the 2 minus 6. What's 1 minus 4? Negative 3. And what's 2 minus 6? Negative 4. Now you'll notice that there's negative exponents there, right? So we're going to change them from the top to the bottom. You got it. So since they're right now on top, because there is no numerator present, I will put them back into the denominator, so it's u cubed and w to the 4th. Because the numbers are small, right? 6, 2, 4, writing them out's fine. If those numbers were quite large, that would not be very efficient, would it? If I had w to the 100, not going to write out 100 w's, right? So having two ways to do the problem, depending on the numbers that you're working with, is sometimes quite useful. Okay, any questions on 9 or 10? Okay, I think that I've got 3 of them on this slide. Yep. All right. Opportunity to try this again. Check it with a neighbor. These are a little bit less cumbersome, a little bit less going on in them than the last two. Okay, just turn it off. Is probably the most complicated one on the screen. If you're stuck on it and you need to just hold off on doing that, it's okay. But once you've done what you can, compare with a neighbor. Okay, do I have a volunteer for number 11? Who's willing to do 11 for me? That's not Macy. She's already done one. 2. She's done 2. Not quite. You're getting closer. Josh, what'd you get on the 11s? Nope. Nope, not right.
Yeah, I was
You're
pretty
treating
sure.
it like it's subtraction.
Yeah.
What do you have on number 11?
That's what I was thinking.
You're close. The closest one I've seen so far. You're really close.
I'm not nowhere near close.
Nowhere near close. You guys are really making 11 so much harder than it is. When I do it, you're going to be like, oh. Does anybody think they have 11? Sure.
Like on 11, what do you multiply? Do you just do the exponents on this?
Not quite. Not quite. Anybody have 11 done? Think that you might have gotten it?
Make sure I do. And then
Yeah. Okay, Sadie, that's not right. Sarah. Sarah's going to do number 11 for us. She has it. Oh, darn. Okay, she's right. It is just -3. Okay, so anything to the power of 0 is 1. So 4W, all to the power of 0 is 1, right? And then you would multiply it by the -3 at the beginning.
that makes so much sense.
Yeah, so it's not as hard as it looked, right? You guys were doing some very creative things with it. Let me do number 12 for you because I filtered around and I'm not sure I saw the right answer on anyone's paper quite right. So I'll do several steps of this. So this is 2 to the -2, u to the -2, and 3 to the -2. Everybody good so far? You're just moving that power into each of the terms. But now I got a whole bunch of negative terms, right? Negative exponents. So what do I do to make negative exponents become positive?
Switch denominators.
I switch. So if it's in the numerator, it's going to switch to the denominator, and if it's in the denominator, it's going to switch to the numerator. So I will now have a 3 squared on top, a 2 squared on bottom, and a u squared on bottom. Okay? What is 3 squared? 9. 2 squared? 4. And then the u squared stays u squared. Is it good?
I had that answer right.
You did. I didn't get all the way over here. Well, good job over here. Well done. Good to see it. Okay, who has 13? Who thinks they have 13? I'm going to look at some papers. You're close. You're close. You've moved it to the denominator, though. Not done yet. What do you have, Jack? Yep, I'm going to let you do it. Do you mind?
Yeah.
Okay, Jack's going to do number 13 for us. Okay, negative exponents. So what did you do with them? Put them in the denominator, right? Yep. And I think is that a 9?
Yes, that's a 9.
Yeah, I thought so. Okay, and then she's added the two exponents from the denominator together. So it's 1 over x to the 9th. I'm going to write it just a little bit bigger. Good? Any questions on that? Let me show you one other way to think about this one, because I saw up here you guys were thinking about it like this. You could actually add the exponents right here. The kicker to remember is that when you add -3 and -6, you actually get -9, right? And then you could switch it to the denominator there as well. Another way of dealing with it. Okay, have a couple more examples I'm going to do with you so we can finish this on off. Number 14, not too bad. Notice they're all y's, right? Okay, so this is just property number 1. I just need to add the numerator, or add the exponents. So I have y to the -1 plus -5 plus 4. This is why we talked about integers early on in this semester, right? I need to add all those numbers together. So it is -1 plus -5 plus -4, or plus 4. It's -2, so this is y to the -2 We're not going to leave negative exponents, so put in the denominator. 1 over y squared. How's that look? Is it okay? Again, it's not the only way to do it. Could you have moved things between numerator and denominator first? You could have. You could have. All right, last example, number 15. Number 15 is actually quite a bit like number 12 over here. I've got a negative exponent on the outside. I've got lots of stuff going on the inside. But I actually have things on the inside that could also simplify among themselves, right? The order of operations actually says that if there's parentheses, I should simplify inside the parentheses first when possible, right? So that's what we're going to do first. We're going to simplify inside the parentheses first. So I'm going to use our properties of exponents to do that. This is x to the power 1. Agreed? Okay. So this is x to the 1 minus negative 2. And then I have y to the 2 minus, this is an understood 1 here as well, right? So 2 minus 1. All of this is to the power negative 3, which we will deal with much later, okay? So, what is 1 minus negative 2? It's 3, right? Minus a negative is addition. So this is plus. So this is x cubed. And then I have y to the 2 minus 1. 2 minus 1 would be just 1. And then now I have this negative 3 power on the outside. Boy, the inside looks a lot better, doesn't it? It's going to be a lot easier to deal with all my exponents when there are fewer exponents to deal with. Okay? So now I can apply this exponent to each of the ones that are inside. So I have x to the 3 times negative 3. You don't have to write that out, but just in case you're curious where my numbers are coming from. And then I have 1 times negative 3. So what's 3 times negative 3? Negative 9. And 1 times negative 3 would be negative 3. Now, I cannot combine the negative 9 and the negative 3 here. Why not? Because the bases are not the same. Do you guys see that?
Yeah.
So don't go combining exponents just because they're there. You still have to have the same bases, and I don't. But what I can do is I can get rid of the negative exponents by doing what? Put them on the denominator. So this would be 1 over x to the 9th, y to the 3rd. Any questions? Okay, to avoid having you move too far, I'm going to pass out. Stop it. Hang on.